Okay, welcome to the first spotlight session of the day, and the first speaker is Miles Lopes, who is going to tell us about residual bootstrap for high-dimensional regression.
So thank you. My name is Miles Lopes. I'm a PhD student at UC Berkeley in statistics, advised by Peter Bickel. The motivation for my work comes from the fact that in high-dimensional statistics, inference problems have been relatively underemphasized as compared to prediction and estimation. And by inference, I mean problems involving hypothesis testing and confidence intervals. So the bootstrap is a basic approach to inference problems, but in high dimensions, there are still many open questions as to when it works and when it doesn't. The particular situation I'm interested in is the high-dimensional linear model, where the number of dimensions p is proportional to the sample size n. And what I'd like to know is, when does the residual bootstrap approximate the laws of contrast? That is, statistics of the form C transpose beta hat minus beta. Okay, so just to remind you how the residual bootstrap works, consider equation 1, which holds whenever we use least squares to estimate beta. What this shows us is that if we could sample directly from the noise distribution, then we could sample from the left-hand side and we would be done. Of course, we can't do that, so what the residual bootstrap tries to do is to resample from the residuals as a way of getting approximate samples from the noise. Okay, in low dimensions, this works well, but in high dimensions, least squares overfits, and what that means is that the residuals are too small. Okay, so as a way of preventing overfitting, it's natural to consider regularization, such as ridge regression, and it turns out that when the design matrix is approximately low rank, the residuals based on ridge regression are a good proxy for the noise. Okay, to specialize this idea a little bit further, I want to consider contrast of a particular type, namely xi transpose beta hat minus beta, and these are the contrasts that arise when you want to set confidence intervals for mean response values. That is the expected value of the yi. What's interesting about this example is that in the 1980s, Bickel and Friedman showed that in high dimensions, the residual bootstrap based on least squares fails in general to approximate all such contrasts. The contribution of my work is that I show that ridge regression can be used essentially to fix this counterexample in high dimensions. So to state the result informally, suppose we work conditionally on a Gaussian design and that the dimension is strictly less than n, but p over n is still bounded away from 0. Okay? Then for most realizations of x, the residual bootstrap based on ridge regression works simultaneously for all contrasts of this type. For more details, my poster is number 49. Thank you.
Thank you, Miles. And next we have Brian McWilliams, who's going to tell us about fast and robust least square estimation.
Thanks very much. Good morning. So this is joint work with Gabriel Krummenacher, Mario Lucic, and Joachim Buhmann at ETH Zurich. So we consider a linear model where the response variable y is generated as a noisy linear combination of the true parameter vector beta. Crucially, however, we do not observe the true covariate z, but instead we see x, some of whose rows might be corrupted, as shown in this diagram. This setting accounts for noisy or error-prone measurement process. Unfortunately, the least square solution in this scenario is also biased. In an attempt to overcome this bias, we ask which observations make an important contribution to the solution. The concept of leverage is well known and behind many recent randomized least squares algorithms. The leverage of the ith point is simply the ith diagonal entry of the hat matrix. Looking at the top histogram of leverage points generated under the corrupted observation model, we see that the corrupted and non-corrupted points both have a symmetric and light tail distribution, which makes leverage useless for distinguishing these points. Instead, we consider a notion called influence, which is defined as the squared L2 difference between the standard OLS estimator and the one computed by leaving out the ith estimate. And this can be computed in closed form. Looking at this, at the second histogram, we can see that non-corrupted points have influence close to 0, whereas the distribution of corrupted points is far more heavy-tailed. This suggests that influence might be used to identify corrupted points. So finally, we propose a simple randomized algorithm. We subsample a small number of observations from the dataset with probability inversely proportional to influence. We compute the influence-weighted subsampling estimator by simply solving least squares using the smaller dataset. We prove that the IWS estimator has smaller bias and variance compared to OLS in the corrupted setting. However, because it requires the full OLS solution as a starting point, we propose an approximation based on fast Johnson-Lin and Strauss projections, which is cheaper to compute. So we started this work at last year's NIPS, so naturally we applied IWS to the problem of predicting the delay of commercial flights in the US. We compare the prediction error in minutes obtained by the full OLS solution, which is the constant line, and its approximation based on leverage sampling. For increasing subsamples, this converges to the biased OLS solution. On the other side, we show IWS and a fast randomized approximation to this, and as we take more subsamples, these converge to an error smaller than the OLS, with smaller error bars confirming the theoretical results. For more information, please come and see the poster. Thank you.
Thank you, Brian. Next, we have Rose Yu, who's going to tell us about fast multivariate spatio-temporal analysis.
Hi, my name is Rose. This is joint work with my lab mates Muhammad Taha Bahadori and my advisor Yan Liu. We're here to present a simple and fast solution to a series of tasks in multivariate spatial-temporal data analysis, such as co-kriging, which is to estimate the temperature of snow cover at unknown locations, or forecasting, which is to predict the user's future check-ins in Foursquare. Accurate and efficient modeling of the data require us to capture the complex spatial-temporal correlations in a scalable way. Existing solutions impose strong assumptions on the correlation via variogram or covariance functions. In addition, the parameter learning for those statistical models is computationally expensive, making them infeasible for the large-scale applications. To solve the problem, we know that the multivariate spatial-temporal data can be naturally represented as a three-mode tensor. Therefore, we propose a low-rank tensor learning framework to capture the correlation, such as spatial clustering or shared latent structure among variables. Our approach follows the local and global consistency design principles. By local consistency, we assume the data in the adjacent locations are similar. By global consistency, we mean the data on the same shared latent structures are similar. Using the co-kriging task as example, we formulated as a tensor completion task, where we're interested in learning a tensor W, which minimizes the difference from the data X at observed location set omega. We enforce local consistency via the Laplacian regularizer L, and the global consistency via the tensor low-rank constraint. In summary, we propose a unified low-rank tensor learning framework for two central tasks in multivariate spatial-temporal data analysis. We propose a simple and fast greedy algorithm with theoretical guarantees. Compared with baseline, our method is not only faster, but also more accurate. For more details about our approach, please drop by our poster at 103. Thank you very much.
Thank you, Rose. Next, we have Pranith Netrapalli, who's going to tell us about non-convex robust PCA.
Hi, thank you. This is joint work with Niranjan, Sujay Sanghavi, Anima Anandkumar, and Pratik Jain. The problem we consider is that of robust PCA, where we are given a low-rank matrix that's corrupted with sparse perturbations. And our task is to recover the underlying low-rank matrix exactly from this perturbed matrix. This problem has a lot of applications, such as video surveillance and graphical model selection and so on. For instance, in the video surveillance problem, each column of this matrix corresponds to a frame. The low-rank matrix corresponds to the background part, which does not change much over time. And the sparse part corresponds to the moving objects that are in the foreground. So the low-rank plus sparse decomposition gives us a way to do the background-foreground separation, which is important for surveillance purposes. The state-of-the-art approach for solving this problem has been based on convex relaxation. However, the convex relaxation-based approach is computationally very expensive and does not scale to very large-scale problems. In this work, we propose a very fast and efficient non-convex optimization based iterative algorithm to solve this problem. Our algorithm maintains an estimate of the low rank part and the sparse part in each iteration and updates them by projecting them alternately onto the set of low rank matrices and that of sparse matrices. Note that both these sets are non-convex sets. However, projection onto these sets can be done very efficiently using PCA and thresholding respectively. Our main result is that despite involving projections onto the non-convex sets, we can guarantee that our algorithm converges to the true global optimum in a very efficient manner. In particular, our algorithm is near optimal, both statistically and computationally. Moreover, it's much faster than the convex relaxation-based approach and can scale to very large-scale problems. The key technique that we use in obtaining our results is a new way to bound perturbation in eigenvectors, which goes well beyond those that we obtain by just using perturbation of eigenvalues, which has been a standard way to obtain such bounds. For more information, please come and see us at our poster tonight. Thank you.
Thank you, Pranith. And now we have Chen Zhang, who's going to tell us about provably optimal algorithm for crowdsourcing.
Good morning. My name is Chen. I'm going to talk about the optimal algorithm for crowdsourcing. This is a joint work with Chen, Dongyong Zhou, and Michael Jordan. Our poster is on Wednesday night, number 95. Crowdsourcing is an important problem. Suppose that we want to do supervised learning on a data set, but we don't have labels on the data. By using crowdsourcing, we can employ the non-expert workers to label the data items for us. Every worker gives noisy labels to a subset of items, and different workers have different accuracies. The following table gives a simple example with 5 items and 5 workers and their labels. The goal of crowdsourcing is to infer the true label of items, as well as estimating the true accuracy of workers to evaluate their performance. The classical approach for solving this problem is to assume a generative model and estimate the model parameters by maximizing log likelihood. This is usually implemented by running an expectation maximization algorithm. The EM algorithm first initializes the true label estimate by using some heuristic approach. Then it fixes the true label and estimates the worker accuracies by maximizing the log likelihood of the model. Then it fixes the worker accuracies and re-estimates the true labels also by maximizing the log likelihood. These 2 steps are alternatively executed until convergence. It is observed in the practice that the EM algorithm converges fast and robust, but its performance sensitively depends on the initialization of the algorithm. Since the log likelihood function we maximize is not a concave function, if we initialize somewhere close to local maximum, then the EM algorithm will converge to this local maximum, making the solution suboptimal. Our first contribution is to propose an algorithm based on the spectral method that is provably consistent. It means that as the number of observations goes to infinity, the estimation error is guaranteed to go to 0. However, the convergence rate of the spectral method depends on the condition number of the problem, which might be a large constant. This makes the convergence slow. It is also observed that the numerical stability of the spectral method is not as good as the EM algorithm. The following picture characterizes the benefit and disadvantages of the 2 approaches. The estimation error of the EM algorithm goes down quickly, but it doesn't necessarily go to 0. On the other hand, the estimation error of the spectral method converges to 0 eventually, but the convergence is slow and not as robust. Our main contribution is to propose a simple combination of the spectral method and EM algorithm such that the optimal convergence rate is guaranteed for the crowdsourcing problem. For more details, please come to our poster number 95. Thank you.
Thank you, Chen. And finally, we have Taylor Berg-Kirkpatrick, who's going to tell us about unsupervised transcription of piano music.
Hi, I'm Taylor Berg-Kirkpatrick, and this is joint work with Jacob Andreas and Dan Klein at UC Berkeley. I'm going to tell you about unsupervised transcription of polyphonic piano music. So this is a transcription task. The input is an audio recording of someone playing an acoustic piano, And the output that we're trying to transcribe to is something like sheet music, which looks like what I'm showing here. In this particular sheet music that I'm showing, you can see that multiple notes are being played at the same time. That's called polyphony, and it's part of what makes this problem really hard because it gives rise to a source separation problem. So what happens when you play a single note on the piano? Well, look on the bottom left, playing this particular F note. If you played it, you'd hear something like this spectrogram that I'm showing in red here, which is plotting frequency as a function of time. This spectrogram is actually the outer product of two different things that we don't know ahead of time. The first, on the top in blue, is the temporal response of this particular key, which has to do with how the hammer strikes the string. The second thing, which is on the left in blue, is the frequency response of this particular note, which has to do with the acoustic properties and the kind of resonances within the particular piano. So these are parameters of the recording environment and of the piano that we don't know ahead of time and that we're going to have to learn. So here's how our model works. I'll tell you very quickly, just going through it top down. First thing that happens is we generate the discrete symbolic musical structure. This is actually the sequence of events that corresponds to the final transcription. Conditioned on that discrete structure, we generate a time series of activations for the particular piano string. This is the volume coming off of that string as a function of time. Now, conditioned on the activations for that string, we actually generate the component spectrogram from that string, and this is like what you would hear if you could only hear that particular string on the piano keyboard. Okay? And of course, all those things are happening in parallel for all the strings inside the piano, and the way they produce the observed input, the spectrogram, the total spectrogram, is the component spectrogram summed together. And so down here in red, that's the only observed random variable in the model. So kind of the three hard things, the adapting to the piano and the acoustic environment, doing the source separation, and taking all this continuous input structure and converting it into something discrete is something that we handle in a unified way via inference in our model. This approach works well. Compared to the previous state-of-the-art, we're actually getting a 42% relative reduction in error. Our system gets an overall F1 of 82.1 on a standard corpus of real kind of virtuoso classical music on a real acoustic piano. See what that looks like. On the top, here's a reference example. Next to it, our prediction, which is overall pretty accurate. Makes a couple of errors. They're actually musically consonant, which is an interesting property of the system. Come see our demo. It's happening at 7 p.m. You can play the piano live, and we'll transcribe live. It's cool. And also, we have a poster happening at 7 as well. Thanks very much.
Thank you, Taylor. This concludes our spotlight session. Let's thank all our speakers again.
So coffee now and back here at 11 o'clock.